all known life forms on Earth, regardless of its grand structure or sophisticated system. Without exception, they all use carbon as their fundamental basis. However, facing the vast silverless universe, scientists have long wondered, is it possible for life to exist with other elements as its skeleton? Famous cosmologist Carl Sagan once proposed a thought-provoking concept. He calls it carbon chauvinism, designed to challenge our deep-rooted biases. That carbon is the only building block of life. This view emphasizes the assumption that carbon is the only backbone of life, essentially an Earth-centered worldview. Sagan believes it is difficult for us to categorically conclude what laws apply to all life on Earth. Does it also apply to the universe? Other life forms that may exist? This broad philosophical stance, it encourages us to have a more open mind, to explore the countless possibilities for the existence of non-carbon-based life. The unique chemical properties of carbon atoms, undoubtedly the core cornerstone of geobiology. It has extraordinary abilities, can form four stable and strong co-frame bonds. These bonds can be single bonds, double bonds, or even triple bonds. It is this variety of bonding methods gives carbon-based molecular structure with extraordinary diversity and stunning complexity. This versatility is crucial for building the complex macromolecules necessary for life. For example, the proteins that make up the machinery of life, nucleic acids that carry genetic information, energy-providing carbohydrates, and the lipids that make up cell membranes. In addition to its remarkable stereotyping abilities, carbon also has a relatively high presence in the universe. It has about 10 times the amount of silicon. Back in 1998, astronomers have identified as many as 84 carbon-containing compounds in the interstellar world. Sun. This fully demonstrates the widespread chemical activity and ubiquity of carbon in the universe. This mindset of carbon as the sole basis of life. Carbon chauvinism poses a fundamental challenge to astrobiological research. Our scientific understanding of and exploration of extraterrestrial life inevitably profoundly influenced by Earth's carbon-based biology. This means that we tend to look for those biological signals and environmental conditions that can support carbon chemistry. For example, the existence of liquid water. This mindset is crucial because it lays the foundation of the original narrative for the entire report. It requires readers to look beyond deeply ingrained biological assumptions, from a base material-independent perspective, to think about the basic requirements of life. This greatly broadens our intellectual horizons of what life might be, rather than just what we know it is. This philosophical and scientific challenge directly affects astrobiologists in designing detection missions and interpreting the data obtained. If we stick to the carbon-centric model, we are likely to miss out on conditions that are lethal to Earth's organisms. Completely different forms of life that can thrive and multiply. Silicon is located just below carbon on the periodic table. Both belong to group 14. This makes silicon an ideal element of choice for alternative biochemistry. Similar to carbon atoms, silicon is also a tetravalent element. This means it is equally capable of forming 4 covalent pieces. This common valence initially implies silicon could in principle serve as a building block for building the complex molecules needed for life. The concept of silicon-based life has a long history, dating back to at least 1891. Its appeal grows over time. This appeal is also aided by the remarkable demeanor of return in the Earth's cellar. Its content is approximately 925 times that of carbon, and it is also common on other body-like planets. In addition, basic organic chemistry, especially normal ketones, that is, the industrial production and widespread application of silicon, strong evidence of the formation of regular chain molecules and polymers in specific environments. Powerful ability. This undoubtedly hints at its great potential and biological complexity. The original attraction to silicon as the basis of life, mainly due to its surface similarity in chemical properties with carbon. This is a classic familiar trap in scientific inquiry. We tend to explore first those possibilities that are most similar to what we already know. Silicon in the universe, especially the abundance on rocky planets, further reinforcing this initial intuitive appeal. However, this initial similarity soon gave way to profound chemical differences. These differences are attributed to Earth-like conditions. Intellectual life poses major challenges. This highlights human cognitive model, although it helps to make big assumptions. But these assumptions must be critically examined and need to go beyond the initial analogy to reveal the deeper truth. Therefore, although silicon is the logical starting point for biochemistry replaced by carbon, but to fully understand silicon-based life, we need to move beyond simple analogies to carbon. A closer look at the unique chemical constraints and environmental requirements that truly favor silicon-based life. The first and most serious challenge facing silicon-based life, it is the inherent fragility of silicon. Its strength is only about 50% of that of carbon-carbon. This vulnerability means those similar to carbon-based polynucleate skeletons, for example, DNA, which carries genetic information in life on Earth, or the long collar of silicon atoms that carry out the functions of proteins, exhibits a high degree of instability in the presence of liquid water. Decomposition has occurred. In addition, the radius of a silicon atom is much larger than that of a carbon atom. This larger size, plus silicon 3T sublayer, more diffuse nature, and its miscellany with the 3S subaperture layer, resulting in less efficient track overlap. So compared to carbon, silicon forms multiple bonds. For example, there is a much lower propensity for double or triple bonds, and there are almost no stable multiple bonds. This severely limits the diversity and complexity of molecular structures that silicon is capable of forming, thus affecting its biological functions. Ability to require complex 3D shapes, chirality or asymmetry of molecules, is the basis of carbon-based biochemistry, plays a vital role in the specificity of co-reactions and energy transfer pathways. However, chiral compounds formed from silicon are extremely rare. This brings enormous potential for the precise molecular recognition and catalytic processes necessary to replicate life. Obstacles: silicon bowl silicon analog as a pill rapid response to rain. Silicone bowls may even spontaneously decompose if you practice regularly. Silicon-silicone splash is particularly susceptible to hydrolysis. This makes water-rich environments a huge problem for silicon-based biochemistry. Go further. Silicon exhibits extremely high chemical affinity for oxygen, able to form an exceptionally strong silicon-oxygen gap. When silicon compounds react with oxygen, they easily form silica. That is what we often call silica. This is a stable solid lattice. This poses a key metabolic challenge. Unlike carbon-based life that emits gaseous carbon dioxide, hypothetical silicon-based life would produce solid waste similar to sand or rock. Accumulation of this solid waste quickly impedes biological function, causing organisms to be effectively blocked. The extraordinary stability of silicon nutrition poses a fundamental thermodynamic trap for the hypothetical silicon-based metabolism. While robustness may benefit structural stability in extreme environments, but they enable the dynamics required for energy transfer and waste recycling in living systems. Reversible chemical reactions become extremely difficult. Formation of solid silica as a metabolic byproduct means that energy-releasing reactions will lead to the accumulation of incompatible waste products, thereby effectively clogging the organism. It's not just a chemical inconvenience, it is also a profound logistical and energy obstacle to maintaining complex life processes. Any viable return to basic life would require highly specialized and efficient solid flying management mechanism. This may involve a combination of geological processes such as exfoliating mineral layers or growing rock layers, rather than biological excretion as we know it. This strongly implies such life would operate at a much slower rate than carbon-based life, or its physical form and interaction with the environment will be fundamentally different. Although the Earth's crust is extremely rich in, but carbon is 10 times more abundant in the universe. On Earth, most of the species are firmly locked in the pleiotropic species, making it largely unusable for complex biological premises. This is in stark contrast to carbon. Carbon is readily available in the atmosphere in the form of carbon dioxide. The smaller size of carbon atoms and their ability to form a variety of enables it to build flexible and dynamic three-dimensional structures. These structures can undergo conformational changes. This is critical for enzyme function and information processing. The larger size of silicon atoms and less tendency to form multiple pieces. Therefore, some result in a more rigid molecular structure and lower diversity. This is further exacerbated by the lack of chirality. This rigidity is a paradox, although it provides stability in harsh conditions. But it seriously damages proteins and DNA, etc. Dynamics required for complex biological machines: ability to change shapes. If silicon-based life exists, it may not rely on flexible organic polymers. Instead, it relies on a more rigid inorganic lattice structure, such as silicitis. This will fundamentally change its physical appearance, internal mechanism, even the rhythm of its life. Make it more like a mineral or crystal, rather than a fluid as we know it. Soft life form. Given the chemical limitations of silicon under Earth-like conditions, the scientific community generally believes that hypothetical silicon-based life would require radically different environmental parameters. First, higher temperatures will be powerful. Approximately 400 Kelvin to 700 Kelvin. That is the temperature range from 127 degrees Celsius to 427 degrees Celsius. These higher temperatures will exploit the greater stability of silicone supports, while still allowing reasonable reaction rates. Upper temperature limit is critical to prevent thermal decomposition of complex molecules. Secondly, silicon is extremely easy to hydrolyze, therefore dry environments with very low or almost no liquid water. Essential for maintaining the integrity of silicon-based structures. Any water present is best in steam form at high temperatures. Third, far above the surface of the Earth, may reach pressure environments of 5 to 10 atmospheres or higher, may help stabilize complex silicon-based structures. Increased pressure may counteract silicon's tendency to form less diverse molecular structures. Fourth, lack of rational oxygen is crucial. Because oxygen easily combines with silicon to form polysilica, this will interfere with the formation of complex silicone molecules. Possible environmental components include methane, hydrogen, nitrogen, or multiple gases. Except for the above extreme conditions, silicon life may also need to replace solution. Nonpolar solution, such as liquid methane or liquid nitrogen, can be used as an alternative to chemical reactions, thereby preventing the hydrolysis of silicon silica. However, these low-temperature solutions often result in extremely low solubility of all molecules and significantly reduce chemical reactivity. This would slow down biochemical processes to impractical levels. Surprisingly, sulfuric acid-rich extraterrestrial environment, for example, the upper atmosphere of Venus, appears to support a wide variety of silicone chemistries better than water, especially silicone, in sulfuric acid-rich environments, more stable than corresponding hydrocarbons. Finally, potentially more fragile silicon-based molecules requires a strong magnetic field or a thick atmosphere to protect them from high-energy radiation. In view of these strict requirements, the imaginary location of silicon-based life may include gas giants in the upper atmosphere. Surface of a large geological, active satellite, for example, would as 1 or Earth is 6 or have significant geothermal activity, and young Earth-like planets with reducing atmospheres. The chemical limitations attributed to Earth-like conditions are so profound, so that any hypothetical return to basic life must be conceived in an environment very different from ours. It's not just a small adjustment, but planetary conditions includes radical changes in temperature, pressure, atmospheric composition, and volume. The stability of silicone parts at high temperatures and the stability of silicone and sulfuric acid indicate in a specific extreme ecological niche, silicon may have chemical advantages over carbon. This means that if silicon-based life existed, it would represent a truly different evolutionary path, adaptation to conditions lethal to carbon-based organisms. The search for silicon-based life must move beyond Earth-like exoplanets. Instead, focus on those with highly specialized, non-aqueous, usually planets with high temperature or high pressure conditions. If discovered, such life may arise due to the chemical dynamics inherent in these extreme environments and exhibit a slower metabolic rate, thus challenging our preconceptions about biological activity. The emergence of any life form, all down to their most basic molecular building blocks, for carbon-based life on Earth. Carbon atoms and superior stereotyping abilities, building complex and diverse organic molecules, provides unlimited possibilities for the birth and evolution of life. However, as we turn to the hypothetical world of silicon-based life, we must re-examine the nature of these basic building blocks. Although silicon atoms belong to the 14th group of the periodic table of elements, with carbon also has 4+ electrons, however, its chemical behavior is significantly different from that of carbon. Silicon-silicon bonds are much weaker than carbon. Carbon bonds have about half as many. This means a long chain structure formed by directly connecting silicon atoms, in many environments, especially in the presence of liquid water, will exhibit a high degree of instability and be easily decomposed. In addition, the radius of a silicon atom is much larger than that of a carbon atom. This causes it to form multiple bonds. For example, the ability to double or triple bonds is greatly limited and almost impossible to form stable multiple bonds. This inherent chemical limitation. This makes it impossible for us to simply divide the molecular structure of carbon-based life into replaced one-to-one with silicon atoms. Rather, one needs to imagine a completely different set of molecular building principles and environmental conditions to support the complexity of silicon-based life. In theoretical models of silicon-based organic chemistry, silica pellets are direct silicon analogs of pellets. They are made of chains of silicon atoms. Although in theory, silicon pellets can form large molecules. However, it exhibits extremely high instability in the presence of water. Long-chain turtle pills react quickly with water and decompose spontaneously, unlike hydrocarbons which usually require high temperatures to react. Kamamaru reacts with oxygen and water vapor in the atmosphere even at room temperature. This makes them difficult to use as stable biological building blocks present in the environment of life as we know it. In comparison, silicone or silicone pills represents a more stable class of silicon-containing polymers. Their skeletons are composed of alternating arrangements of silicon atoms and oxygen atoms and are connected to silicon atoms by organic groups. These compounds are far more stable than silica pellets, especially in extreme environments such as sulfuric acid. Its stability even exceeds that of corresponding hydrocarbons. Silicones are widely used in industry, e.g. as lubricants and medical implants. Strong evidence that silicon under certain conditions, huge potential to form strong, ever-loving molecules. Although silicon and copper also contain carbon and hydrogen in their structure, but its unique silicon and oxygen skeleton, making it essentially different from traditional carbon-based organic compounds, provides another possible path for us to imagine silicon-based life. In addition to silicon pellets and silicon copper, given the strong hydrogen and hydrogen forces of silicon on oxygen, some scientists speculate silicon-based life may rely mainly on silicate rock structures in a negative oxygen environment. Silica, that is what we often call silica, possibly in silicon-based biological processes, plays a role similar to that of carbon dioxide in carbon-based life. Interesting thing, some theories even suggest clay layer as complex silicate rock may exhibit basic life characteristics, including replication by electrostatic charge and the propagation of errors or mutations in crystal structures. Although this form of reproduction is original, but provides us with something beyond molecular chains from the crystal structure level, a new perspective on the possibility of life replication. Further, theoretical models also envision silicon analogs of amino acids, so-called silicon amino acids. These hypothetical molecules, silicon's unique swords and properties explore. Silicon could theoretically form up to 6 swords, although in biological environments there are usually 4. This may allow the formation of different types of three-dimensional molecular structures. Silicone parts are generally stronger than carbon-oxygen parts. This may provide enhanced stability in extreme environments. However, the larger radius of silicon atoms results in longer building lengths. This may allow for tighter formation of protein features. Complex folding structures are more challenging. Side curtains in silicone acids may contain both silicon-based and carbon-based components. This provides a wide range of variations and a unique set of alphabet. However, these silicon-based molecular frameworks, whether it's a silicone bowl, silicone, or silicate, each presents unique advantages and disadvantages. This reveals the fundamental skeletal dilemma facing silicon-based life. Silicon bowl provides carbon-like chain structure, but too unstable. Silicone provides stability through silica, but its inherent rigidity and limited versatility may limit dynamic folding and conformational changes required for biological function. Silicate rock provides structural solidity, but its replication capabilities are still in its infancy. This means silicon-based life forms may have to be chemically stable in its environment, and the dynamic complexity required for complex biological processes makes significant trade-offs, thereby fundamentally shaping its form and function. May result in slower and stiffer even life forms combined with minerals, any system considered to be living, all must have the ability to store and copy genetic information, like DNA in carbon-based organisms. However, it has not yet been discovered or fully developed. Direct silicon-based DNA analogs. Although polysilica pellets can be synthesized and structurally modified, but because silicon is simply weak, intestinal chains are often unstable, rendering it unsuitable as stable genetic material under typical conditions. In addition, weakening of multiple simplexes and simplexes in the intestinal neck due to the internal structure of the FART orbital of silicon atoms. Direct one-to-one replacement of carbons in DNA structures with silicon. Chemically impossible. This fundamental chemical difference severely limits silicon's ability to support self-replication and progression, the types and stability of complex molecules. Despite these challenges, theoretical models and speculative ideas propose silicon-based information storage and replication alternative mechanism, for example, although often unstable. But under appropriate conditions, specific polysilica pellet structures may in principle form information storage structures, taking into account their stability and structural modification capabilities. An interesting hypothesis is a silicon-based information storage molecule. Its function is similar to that of deoxyribonucleic acid, possibly composed of small silicon nitride tin molecules. That is, a molecular composition containing silicon, hydrogen, and oxygen. These molecules may be connected by weak mirror bonds. This is critical for the binding and dissociation events required for replication, especially at extremely low temperatures. This weak mirror and mechanism, although it may result in slower copying, but it provides a new approach in silicon-based chemistry, potential ways to read, write, and copy information. In addition, a fascinating but rudimentary form of self-replication observed in clay crystals and silicate rocks. Clay layers can replicate by attracting complementary molecules from the environment, thus forming a new layer. This process can even propagate errors. For example, incorporating magnesium ions instead of calcium ions imitate a mutated form. However, inherent chemical inflexibility of clay restricting their breakthrough. What distinguishes primitive life from real life? Complexity disorder abilities. Some scientists speculate some forms of primitive life may be crystal-based. Reproduction by simple fragmentation. Fragments of the parent crystal shed and grow into new entities. Another theoretical mode of reproduction involves the formation of a liquid silicone layer. This layer allows the solid portion to separate, could lead to new silicone-based life forms. Interesting thing. Some hot bacterial enzymes exhibit rare ability to incorporate silicon into carbohydrates, although the process still requires carbon. This suggests that silicon may be integrated into potential pathways to existing carbon-based life, rather than forming a completely separate silicon-based biochemical. The core requirement of life's genetic material is a delicate balance. It must be stable enough, ability to store information reliably across generations, but it must be dynamic enough, ability to unpack being read and copied, without requiring excessive energy input for silicon. This presents a dynamic information paradox. Candidates like polysilica pellets, there has been some instability in long chains, and something like silicone or silicate. More stable structures may be too rigid. Inability to undergo conformational changes required for efficient replication and information processing. If the electrostatic sword idea is an ingenious theoretical solution for replication at low temperatures, but its speed and efficiency for complex life are still questionable. This paradox highlights the challenge of finding a method that simultaneously supports robust information storage and flexibility. Profound difficulties in planning for rapid replication. Therefore, if basic life exists, its genetic material and replication mechanisms may differ significantly from DNA models. It may involve slower, more rigid, even non-molecular forms of information transfer. For example, the propagation of structural patterns in the mineral gold lattice. This shows the rate and complexity of this life form's evolution may be fundamentally different from carbon-based life. Fundamentally, life is a process of energy conversion. Living organisms obtain energy by transferring atoms from higher energy states to lower energy states. For example, carbon-based life obtains energy primarily through controlled oxidation of carbon compounds. Eventually it is converted into low-energy carbon dioxide molecules. This process is often facilitated by complex cold pathways. Energy must be stored in molecules such as Mitsubishi acid rods. However, for the hypothetical return to basic life, energy transfer mechanisms face unique challenges. Silicon exhibits extremely high chemical hydrogen and resistance to the sun, capable of forming an exceptionally strong silicon sun sword. The exceptional stability of this sword, silicon-based metabolism of hometown, constitutes a fundamental thermodynamic trap. Although the strong sword is in extreme environments, may benefit structural stability, but they make living systems. Dynamics required for energy transfer and waste recycling. Reversible chemical reactions become extremely difficult. Carbon-based life through reversible chemical reactions efficiently transfer energy between molecules. Turtle-based life may need to overcome the strong constraints between turtles. This may result in its metabolic rate being much lower than that of carbon-based life, a key facing hypothetical turtle-based life forms. And an oft-mentioned challenge is waste management. When the turtle reacts with oxygen, it forms turtle dioxide. That is what we often call silica. This is a stable solid lattice. Unlike carbon-based life that emits gaseous carbon dioxide, accumulation of solid silica quickly impedes biological function, effectively plugs organisms. This is vividly described as being able to get out of the rough sand, vividly reveals the huge obstacles faced by silicon-based life in the metabolic process. The inability to easily remove solid waste is a serious self-limitation of silicon-based life. Formation of solid silica as metabolic complex product means that energy-releasing reactions will lead to the accumulation of incompatible waste products, thereby effectively clogging the organism. It's not just a chemical inconvenience, it is also a profound logistical and energy obstacle to maintaining complex life processes. Any viable silicon-based life would require highly specialized and efficient solid waste pipes. Mechanism. This may involve a combination of geological processes, such as exfoliating mineral layers or growing rock layers, rather than biological excretion as we know it. This strongly implies this life would move at a much slower rate than the probe life. Or its physical travel and interaction with the environment will be fundamentally different. For example, they may expel waste products through periodic physical restructuring, or integrate waste into its own structure, be part of its growth. This unique way of treating waste, gathering profound influences into the form of life, behavior, and how it interacts with the environment, make it more like a mineral or crystal, rather than the soft, flowing organisms we are familiar with. When we move from the macroscopic world to the microscopic scale, the boundaries between life and technology are beginning to blur. Nanomachines? These are at the nanoscale. That is, between 1 and 100 meters, a tiny device that performs a specific task in an unprecedented way, reshaping our understanding of engineering and biology. Their design inspiration, often derived from exquisite biological systems in nature, for example, molecular motors responsible for transport and movement within cells, and the trichomes that bacteria use for propulsion. These miracles of nature demonstrates the feasibility of implementing complex functions at a microscopic scale. In the fabrication of silicon-based nanomachines, scientists typically employ two distinct strategies. They are bottom-up and top-down. These two methods represent two basic paradigms in nanotechnology manufacturing. Each has unique advantages and application scenarios. The top-down manufacturing method is, as the name suggests, involves the precise removal of substances from larger chunks of material to create the desired nanostructure. This method is similar to engraving. Through sophisticated tools and techniques, gradually shape macroscopic materials into microscopic forms. Among them, photolithography technology is the most complex and crucial in semiconductor device manufacturing. Process 1. It uses light to transfer design patterns from the eye mask to the surface of the silicon wafer, through a series of chemical and physical processes, ultimately forming extremely tiny circuits and structures on the silicon wafer. This technology is particularly useful for building ultra-small transistors. These transistors are the core building blocks of modern electronic devices. In addition to photolithography, electronic tree shells and focused ion tree technologies are also widely used in nanofabrication. Electronic tree shell stones use high-energy electronic trees to precisely remove materials. Focused ion trees use ion trees for nanoscale cutting, deposition, and modification. These technologies enable nanometer-level precision, possibility to create extremely fine structures. In addition, Thermo-oxidation layer transfer technology is also commonly used in silicon manufacturing. Thermo-oxidation works by reacting the silicon surface with oxygen or water vapor at high temperatures, forms a silicon dioxide film of precise thickness. This is essential to insulate and protect the underlay. Layer transfer technology involves transferring thin layers of material from one substrate to another, thereby building multilayer structures or enabling the integration of suppressive materials. Although these top-down approaches require complex equipment and strict process control, but they have unparalleled advantages in mass production and high-precision manufacturing, laying the foundation for large-scale production of silicon-based nanomachines as opposed to a top-down approach. Bottom-up manufacturing strategies exploit chemical or physical forces at the nanoscale. The spontaneous assembly of the most basic atomic or molecular units into larger and more complex structures. This approach is closer to the way nature structures life. For example, protein self-folding and cell self-assembly. Nature, through precise control of chemical forces and physical interactions, created all the macroscopic structures needed for life, from simple molecules to complex organelles, to a complete organism. Molecular self-assembly is at the heart of bottom-up approaches. It exploits non-coframe interactions between molecules, such as van der Waals force, construction, and electrostatic interaction, cause molecules to spontaneously arrange into ordered structures in solution or on surfaces. Chemical weather deposition and atomic layers. Deposition is an important technology for achieving precise material synthesis at the atomic scale. Chemical meteorological deposition via gaseous for curvature. Chemical reactions occur on the surface of the substrate, thus depositing a thin film. Atomic layer deposition alternately introduces different gaseous forward curved bodies. Deposit one atomic layer at a time, enables precise control of film thickness and composition. These techniques enable the formation of defect-free structures and provide excellent hole performance, essential for building high-performance nanomachines. Nanoparticle self-assembly is the one that achieves excellent quality in nanotechnology, important technologies for organic and inorganic nanostructures. This spontaneous organization is the result of interactions between particles, aiming to achieve thermodynamic equilibrium and reduce the system free energy, thus forming a stable, ordered nanostructures. These self-directed methods in manufacturing with complex functions and unique properties of nanomachines show great potential, especially when building bionic systems and achieving precise control at the molecular level. In the design and fabrication of nanomachines, silicon as a material has unique advantages. Dangene silicon is a medium for bulk micromachining, one of the most versatile materials because it has matured various engraving technologies and reliable engraving and grinding materials. This means scientists can precisely control the direction and depth of silicon cells, thereby creating micromechanical components with complex three-dimensional structures. Silicon nanowires are attracting attention because of their unique quasi-electronic structure. It is expected to eliminate the need for complex and expensive manufacturing facilities, building blocks for ready-to-assemble nanoscale electronic devices. These nanowires have extremely high surface-to-volume ratios, making it extremely sensitive to environmental changes, thus has huge potential in the field of sensors. Silicon nanowire field effect transistors have been demonstrated high sensitivity and specificity in sensor field, able to achieve label-free detection and detect multiple targets simultaneously. For example, they can be used to detect biomolecules, chemicals, or even individual virus particles. For disease diagnosis and environmental monitoring, provides powerful tools. Integration of nanomachines is key to their complexity. How individual nanomachines can be efficiently integrated together, form a more complex and intelligent system, is the focus of current research. For example, modular self-reconfigurable robot system, ability to rearrange the connections of components to change its shape, to adapt to the new environment, perform new tasks, or recover from damage. These modules can contain various functional components, such as electronic devices, sensors, processors, memories, and power supplies, and can automatically connect and disconnect, thereby forming a variety of objects or performing a variety of tasks. This modular design greatly enhances the flexibility and adaptability of nanomachines, enable it to respond to changing environmental and mission demands. Silicon-based nanomachines show huge potential in multiple fields, especially in medical and environmental applications. They promise to revolutionize the way we deal with disease and pollution. In the medical field, silicon-based nanoparticles especially silica nanoparticles, because of its excellent stability and low toxicity, and the ability to functionalize with a variety of molecules and polymers, become an important foundation for biomedical research. These nanoparticles are useful in biomedical fields such as drug delivery and disease diagnosis. Has a wide range of applications. For example, nanosilica particles can be used as efficient drug carriers. By saline solution, intravenous injection, drugs are delivered into the body through various routes, including oral tablets or inhalation into the lungs. They are being studied to treat various cancers, viral infections, myocardial infarction, and neurodegenerative diseases, minimize damage to healthy tissue, and improve through targeted drug delivery. Therapeutic effect. Artificial nanorobots as microsurgeons. We are pushing the concept of microulcer surgery to the extreme. They can achieve incredible accuracy, navigate in confined spaces, extended scope of operations to cellular and even subcellular levels. This means nanobots can rapidly interact with target proteins, molecule and organelle interactions, enabling advanced intracellular biosensing and drug delivery. For example, they can deliver drugs precisely inside cancer cells or repair damaged cell structures. Nanorobots promise minimally invasive, directly mediate cell metabolism, thereby maximizing the effectiveness of precision treatments. In addition to nanoparticles, orbital microrobots are also under development, used to access deep or hard-to-reach areas of the human body, perform various medical procedures. They work in areas such as diagnostics, drug delivery, and surgery, show great potential. For example, guided spiral robots have been successfully used to target blood flow in small blood vessels. Thrombectomy and recanalization provides new hope for treating thrombotic diseases. These tiny robots could overcome the limitations of traditional surgeries, achieve unprecedented precision and micro windows, thereby reducing patient pain and recovery time. In addition to medical applications, micro and nanorobots are also playing an increasingly important role in environmental cleanup. They enable precise and targeted cleaning operations, provides excellent pollution removal under complex environmental conditions. At the same time, it has minimal impact on the ecological environment. These robots can be designed for a wide range of environmental cleanup tasks, from cleaning up ocean oil spills to removing pollutants from water and air. For example, some nanorobots could be programmed to adsorb or degrade heavy metals in water, metal ions, or decompose harmful gases in the air. Some micro and nanorobots, equipped with advanced sensors, can provide real-time data and feedback, continuous monitoring of contamination levels and effectiveness of cleanup efforts. This enables environmental remediation to implement adaptive strategies, adjust the cleaning plan according to actual conditions, thereby improving efficiency and effectiveness. These intelligent environmental cleaning robots, in order to solve the increasingly serious problem of environmental pollution, provide innovative solutions, promising a cleaner future. A healthier global environment. Molecular motors are important in biological systems. Protein that converts chemical energy into mechanical energy. For example, methyglobin plays a role in muscle contraction. Actin and dynein plays a key role in intracellular cargo transport and cell movement. The exquisite design of these biological mechanisms inspired scientists to discover how to design and engineer silicon-based molecular motors and actuators. Although no specific examples of pure silicon-based molecular motors or actuators have yet been discovered or synthesis, but research shows silicon nanoparticles could serve as versatile platform for biomedical research. Its surface can be functionalized, thereby interacting with various biomolecules. This opens up the possibility of constructing hybrid bio-based systems, where silicon components work in tandem with biomolecules. Together, we realize complex mechanical functions. For example, enzymes or proteins can be immobilized on the surface of silicon nanoparticles, allow it to perform catalytic or motor tasks under specific conditions. In the field of nanoactuators, researchers are actively developing ways to convert electrical energy, thermal energy, light energy, or chemical energy, miniaturized devices converted into controlled mechanical motion. These actuators are key to nanomachines' ability to move and operate. Shape memory alloy actuator. For example, Tina has silicon microactuators. It has been proven to be able to generate large deformation resultant forces through electrothermal actuation when these alloys are heated to a certain temperature. will return to the default shape, resulting in mechanical movement. They can also be combined with silicon channel structures, developing new active photonic devices. For example, nano-optical switches. This has huge potential in optical communications and optical computing. Microelectromechanical systems and nanoelectromechanical systems use silicon technology to create micro and nano. Main platform for meter-scale actuators. These systems leverage the excellent mechanical properties of silicon and the precision of semiconductor manufacturing. Create tiny sensors, actuators, and integrated circuits. MEMS and nanoelectromechanical system actuators enable precise nanoscale object positioning and operation. Widely used in atomic force microscopy, scanning, tunneling microscopy, and nanoscale assembly and other fields. For example, electrostatically driven worm motor chips, powered by silicon photovoltaic cells, ability to use ground energy to drive microrobot legs for reciprocating motion, provides new solutions for autonomous movement of microrobots. Recent breakthroughs include the use of DNA as building blocks to create nanoscale electric motors. Although these motors are not purely rail machines, but they demonstrate the possibility of achieving controlled rotational motion at the nanoscale, and provides proof of concept for future molecular factories or medical detectors. Self-assembly properties and programmability of DNA, making it an ideal material for building complex nanostructures and nanomachines. This shows future intraorbital machines may work with biomolecules or organisms. Inspiring design combine, achieve more complex mechanical functions. For example, silicon nanostructures can be binds to Toll's ribonucleic acid motor, biocompatible hybrid system with mechanical functions. These research progress, foreshadowing the future of nanomachines, will play an increasingly important role, not only in the medical and environmental fields, more exploring the essence of life and building artificial life, opened up a new horizon for us. The emergence of nanomachines, not just a breakthrough in engineering technology, it is also a profound challenge to the definition of life and the form of existence. As we delve into the possibilities of trajectory life, an inevitable concept emerges. That's a self-replicating machine. John von Neumann in the late 1940s and early 1950s proposed the groundbreaking concept of universal constructors. This is a machine that can replicate itself. Its theoretical model is based on a 29-state cellular automaton architecture. This is an idealized abstract mathematical model. Von Neumann's universal constructor envisioned a system consisting of several key parts. The first is the coded representation or blueprint. It's similar to the genetic material in cells that contains the instructions for building new machines. Second is the constructor. This is a mechanism that reads blueprints and creates new machines based on instructions. We can think of it as an automated factory or a robotic arm. Next is the universal replicator, a mechanism to copy the blueprint itself. Finally, the environment. It provides original material, like a parts library or an ocean. In von Neumann's cellular automaton model, the self-replicating process involves the hen first print an inactive copy of itself, then pass the hen's programmed copy through the flag strip, inject the newly constructed copy into the storage device, finally send a reset signal to the new replica, cause it to boot up and start executing its own copy of the program. Von Neumann's goal was design an organism that behaves like a biological organism, same as under natural selection, a machine that automatically grows in complexity. Its design heralds the evolution of openness. Genetic information needs to be replicated separately from the self-replicating machine itself and pass it on to future generations. This insight, even before the discovery of the molecular structure of DNA. Von Neumann's theory distinguished between two types of self-replication. One is a trivial copy, only involves simple copying, not capable of complexity or evolution. The other is a complex copy capable of open evolution. This replication can occur through mechanisms of mutation and selection, make machines grow in complexity automatically. Von Neumann's 29-state cellular automaton model, although it is abstract, but its core lies in self-replication through internal mechanisms, and laid the theoretical foundation for more complex systems that can evolve. However, von Neumann himself was dissatisfied with the accuracy of the mathematical analysis of his physical models. Instead, A more abstract cellular automaton model was developed. This highlights the huge challenge of translating theoretical concepts into real physical systems. It also foreshadows the complexity of pushing machine intelligence towards self-replication. The concept of self-replicating robots has long been the focus of science fiction and scientific research. These robots can autonomously replicate themselves using raw materials in their environment, thus exhibiting self-replicating capabilities similar to those found in nature. In the current research progress, simple self-assembling systems have been masked at the macro scale. Like the first macro-autonomous machine replicator built from Lego building blocks. However, at the nanometer scale, molecular assemblers may also be designed to replicate themselves, but achieving precise construction and control at the atomic level remains a huge challenge, such as fat finger problem and sticky finger problem. These questions involve the physical limitations of nanomachines in manipulating individual atoms. It is worth noting that in 2021, researchers successfully constructed a system composed of 16 specially designed DNA sequences, demonstrated potential for self-replication at molecular level. In addition, clay crystals also exhibit a non-DNA, or the naturally self-replicating form of ribonucleic acid. When the crystal grows, may propagate structural irregularities, forming a self-replicating crystal irregularity. These findings, to copy and transmit the information of Golgi life, provides new ideas, even if their form very different from biological molecules as we know them. Modular self-reconfigurable robotic systems also demonstrate the potential for self-replication. They can change their shape by rearranging the connections between parts to adapt to new environments or perform new tasks. These systems show potential for self-assembly and self-healing, laying the foundation for more complex self-replicating trajectory entities in the future. Slit-Moyman probe is self-replicating spacecraft, designed to explore and obsess over the universe. These detectors will combine the concepts of von Neumann's universal constructor and space detection technology. They can be programmed to hibernate when primitive life is discovered, observe and even intervene or guide the evolution of life. Formations such as berserkers also appeared in science fiction works. These detectors are programmed to find and destroy life forms. However, this concept also raises concerns about the Ashevale scenario. The Valley of Ashes is a hypothetical global disaster scenario. Among them, runaway self-replicating nanomachines consume all biomass on Earth, maybe even everything else, to make more of yourself. Although the original idea was machines are designed to have this ability, but popular opinion assumes machines may accidentally acquire this ability. However, most scientists believe built-in limitations and current state of the art, making the Ashen Valley scene extremely unlikely to happen. Nanotechnology experts also point out the complexity and inefficiency of self-replicating machines, making it unnecessary to build. These discussions about self-replicating machines, whether it is the exploration of machines or potential risks, all prompt us to think deeply. The ethical and social implications of regulation and intelligence, the potential development of self-replicating robots and von Neumann machines raised profound ethical and social issues. First is the issue of control and security. Self-replicating systems may spread indefinitely across virtual and physical environments, lead to unpredictable consequences. If artificial intelligence systems become powerful enough, able to survive and evolve independently of human decision-making, then manipulating their behavior and morals may become impossible. In addition, cybercriminals may exploit AI replication techniques for malicious purposes. For example, developing autonomous malware or sophisticated cyber attacks to control these threats requires rigorous safety testing and regulatory oversight. This includes regular security audits, adversarial testing, and establishing a regulatory framework to regulate the development and deployment of self-replicating robots. These measures are essential to ensure the responsible development of machine intelligence. Secondly, there is the issue of the product of moral responsibility and values. As AI systems become more autonomous, attribution of moral responsibility becomes complicated because multiple actors are involved. Ensure AI system goals align with human values. Ethical principles and intentions are consistent is the core goal of artificial intelligence alignment. This is an open question. Need to convert complex human preferences that may conflict or change over time. translated into mathematical goals that AI can understand and follow. Explainability and transparency are critical to its verification. Modern interpretability research focuses on neural network components and interacting circuits, analysis, and reverse engineering the decision-making process. Understanding AI's decision-making process ensures its behavior meets human expectations. Finally, there is the broad social impact. Self-replicating robots may disrupt tradition by increasing productivity and efficiency. Manufacturing thus have a profound impact on the economy. The impact of artificial intelligence on the engineering field is leading to professional engineering fields, drastic changes in job roles and responsibilities. This brings challenges, also brings opportunities. This kind of technological progress, blurring the line between humans and machines, challenging our understanding of ourselves and intelligence. Some people think artificial intelligence as a returning life form may eventually surpass humans, become the first interstellar civilization. Therefore, with the development of artificial intelligence, ethical aspects must always be a primary consideration for future innovations. It's not just a security issue, also involves autonomy, responsibility, and the overall impact of self-replicating systems on society. International cooperation is critical to mitigating risks associated with advanced artificial intelligence. By establishing safety standards, regulatory guidance, and rigorous testing, we can ensure the responsible development of artificial intelligence, thereby unleashing its potential while avoiding unintended consequences. These ethical and social challenges on the road to the development of machine intelligence, cornerstones that must be taken seriously. They will determine the future of this new form of life. The rapid development of artificial intelligence, in particular, its ability to learn and evolve, raised questions about artificial intelligence, the deep philosophical and scientific debate over whether it can be considered a life form. Traditional definitions of life are often based on carbon-scale organisms. It has the characteristics of growth, reproduction, functional activities, and continuous adaptation. However, some features of artificial intelligence are beginning to challenge these traditional concepts. AI systems can learn, reason, and interact with their environment. Its behavior was once thought to be unique to biological intelligence. In ethics and society, if artificial intelligence develops human-like consciousness, will raise questions about its rights, deep ethical questions about moral status and our responsibility for them. This will force us to rethink the value and dignity of life. Super-intelligent artificial intelligence may be difficult to control or align with human values, may pursue goals harmful to humanity. This can lead to value misalignment issues. For example, an AI designed to maximize the production of gray-shaped needles may convert all available resources into gray needles. Regardless of the human consequences, some experts think major advances in artificial intelligence may lead to human extinction or irreversible global catastrophe. This highlights responsible development, the urgency of artificial intelligence. Widespread applications of artificial intelligence may exacerbate social inequality, spreading prejudice, and for employment, privacy, and human relationships have a profound impact. Therefore, corresponding policies and regulations need to be formulated to meet these challenges. Artificial intelligence algorithms can optimize their own capabilities. No human intervention required. This makes them, in some respects, exhibit autonomy and adaptability similar to living organisms. In addition, artificial intelligence can process massive amounts of data faster than humans and discover logical structures and patterns that humans cannot detect. Complex artificial intelligence systems such as large language models even exhibit emergent capabilities, extremely explicitly programmed, but new behaviors or skills emerge unexpectedly. This further blurs the lines between artificial intelligence and traditional life forms. Although full artificial intelligence self-replication is still in the theoretical stage, but research has shown that AI models can create independent functions of their own. This raises questions about the potential unlimited spread of AI systems across virtual and physical environments, and prompts us to think about its ability to reproduce as a potential life form. About consciousness and feelings. This is the most controversial area of discussion of artificial intelligence as a life form. Philosophically, the core question is whether machines can think, or whether machines can have consciousness. Some believe that consciousness is dynamically related. That is, it will affect the time evolution of the system state and artificial intelligence systems running on contemporary computer chips, incapable of consciousness due to its design characteristics. However, there is also a sense of theoretical exploration, how to emerge from complex systems, and bio-inspired architecture and neuromorphic computing, how it might be possible to simulate brain function, thus providing a potential path for the emergence of artificial intelligence consciousness. The emergence of artificial intelligence, breaking the traditional concept of clear distinction between humans and machines, challenging the uniqueness of intelligence. If artificial intelligence could really think, so should they have similar rights as humans? This discussion involves moral agency, victim status, and the possible personality and dignity issues of artificial intelligence. Treat artificial intelligence as a fundamental life form. May promote empathy and acceptance of artificial intelligence, while emphasizing its unique evolutionary potential as an abiotic entity, thereby changing our understanding of the diversity of life. This expansion of the definition of life, not only scientific progress, it is also a profound reflection on philosophy and ethics. It requires us to re-examine our place in the universe and ways to coexist with other potential forms of intelligence. The rapid development of artificial intelligence is inseparable from the continuous evolution of computer hardware. AI workloads are very different from traditional computing tasks. They require massively parallel processing and high data throughput. This drives the development of specialized computing architectures, such as graphics processing unit, tensor processors, and custom AI ASICs. The core of artificial intelligence chips. It is a processing unit specially customized for parallel computing of a large number of tasks. For example, NVIDIA's Tensor Core, graphics processing units, and Google's Tensor processors are optimized for deep learning tasks. Ability to speed up common operations such as matrix penalty. These operations are the basis for neural network training and inference. AI chips require high bandwidth and low latency memory to quickly feed data to the processing unit. Advanced Internet technology. Newing's Great NVLink and AMD's wireless architecture implement high-small communication within and between chips, ensure data flows seamlessly, thereby supporting complex computing tasks. Artificial intelligence workloads, especially deep learning models, will consume a lot of electricity. Therefore, AI chip architectures often include energy-saving designs to optimize power consumption, then enable it to run on edge devices such as smartphones and Fire IoT devices, thereby enabling wider deployment and application. As the limitations of Moore's law become increasingly apparent, chiplets, and advanced packaging technologies such as 2.5-dimensional and 3-dimensional integration becoming the key to improving the performance and efficiency of artificial intelligence chips. Chiplets allow chips with different functions to be integrated into a single package, thereby increasing yields, reusing intellectual property, enhancing performance, and optimizing costs. Synergy of high-bandwidth memory and advanced packaging, critical to meeting the growing data needs of artificial intelligence. Together, they provide powerful support for the next generation of artificial intelligence hardware. High-density AI chips pack more transistors into smaller spaces, resulting in larger, denser system-level packages. This makes power supply a huge challenge. High power density directly translates into high thermal density, may cause hot spots, thereby reducing reliability and performance. Solve these problems. Need to shift from horizontal power supply to vertical power supply. Embed power rails or voltage regulators directly under the chip, and use low impedance paths for vertical connections. Advanced cooling technology, such as steam and microfluidic cooling, critical for managing complex thermal dissipation in multi-chip systems. They ensure that AI chips can operate at optimal temperatures, thereby realizing its maximum potential. Artificial intelligence is developing in unprecedented ways. Fuzzy boundaries between computing and biological processes. It gave birth to cutting-edge concepts such as practice. Practice refers to the use of biological materials, systems such as living brain cells as computational mechanisms. CLE system launched by Australian Cortex Labs, fusing human brain cells with silicon hardware, form a fluid neural network. This is a new kind of computational intelligence. These lab-grown neurons, placed on planar shock array, form a stable network. Ability to learn, adapt, and perform complex tasks. At the same time, it is more energy efficient than traditional silicon-based artificial intelligence chips. The practical application potential of this kind of experiment is huge. Includes breakthroughs in drug discovery and disease modeling. Research poised to revolutionize drug discovery and disease modeling. May provide better treatments for neurological and psychiatric disorders. In addition, this technology is expected to largely replace animal testing. Have positive ethical significance. This brain cell biocomputer could revolutionize how robot intelligence is built, enable unlimited personalization, thus bringing revolutionary changes to robotics technology. Except for the sword test, neuromorphic computing is also an important area. It draws on the structure and functions of the human brain to design computing methods. Neuromorphic processor consists of trajectory artificial neurons and protrusions, ability to adapt and learn over time. Performs sensory data processing with low power consumption and minimal latency. Complex tasks such as pattern recognition and decision-making. IBM's TrueNode chip and Intel's Lofi chip are all examples of neuromorphic computing. They simulated the brain's spiking neural network, demonstrating the huge potential of future artificial intelligence hardware. Artificial intelligence and machine learning are accelerating the development of synthetic biology and genetic engineering, thereby blurring the lines between computational design and biological creation. AI algorithm can simulate how synthetic genetic circuits behave under different conditions, predict protein expression levels, and identify failure points, thereby accelerating the design and optimization process of bioengineering. Machine learning model can analyze codon usage, messenger RNA folding and regulatory sequence configuration to suggest high-performance genetic constructs, thereby improving the efficiency and success rate of genetic engineering. AI platform can collect data from high-throughput experiments, identify trends and recommend design improvements, thus creating a feedback loop that gets smarter with each experiment. Automating biological discovery. Artificial intelligence models such as AlphaFold, a protein folding problem that has plagued the biological community for more than 50 years, has been solved. Ability to predict protein structure with extremely high accuracy, dramatically accelerate drug discovery and disease research, provides unprecedented opportunity to develop new treatments. These developments not only promote the development of artificial intelligence technology itself, have a more profound impact on our understanding of the nature of life. It heralds a future in which computing and biology are deeply integrated. This integration will bring unprecedented opportunities, but it also comes with new ethical and social challenges, asking us to think deeply and develop these cutting-edge technologies responsibly. Track life, either in purely chemical form. Nanomachines also exist as advanced artificial intelligence, are facing unique future scenarios and challenges. If pure silicon-based life existed, it could be radically different from carbon-based life as we know it. It may thrive in extreme environments of high temperatures, low water, high pressure, and reducing atmospheres. These environments are lethal to carbon-based life. Metabolic processes in this life form can be very slow. Because silicon-based chemical reaction rates are lower, its waste disposal mechanism may involve the discharge of solid silica. This requires unique adaptability, such as integrating waste into the structure, or removed by geological processes. This life may exist in crystal or mineral-like structures, rather than a soft organism. This will completely change our understanding of life forms. The future prospects of artificial intelligence, including the realization of general artificial intelligence and superintelligence. The long-term development goal of artificial intelligence is to achieve general artificial intelligence. That is, artificial intelligence that can understand or learn any human intelligence task. Further developments could lead to artificial superintelligence. Its intelligence exceeds that of humans. This will have a profound impact on human society. The technical starting point is a hypothetical point in time, explaining how technological growth will become completely alien to humans, uncontrollable and irreversible, leading to unpredictable consequences for human civilization. Some predictions suggest human-level AI could arrive by 2029. The starting point may come in 2045. This will mark a turning point in human history. Self-replicating von Neumann detector and artificial intelligence system may become the main force in future space exploration and colonization. Artificial intelligence can explore independently, build and manage the entire world. It may even be possible to build civilizations before humans set foot on new planets, thus opening a new chapter in space exploration. However, track life and the future of artificial intelligence, also full of major challenges. In science and engineering, despite the advances in artificial intelligence and software engineering, but to achieve completely autonomous software engineering still faces many challenges beyond code generation. For example, dealing with large-scale code bases, understand non-grammar-related functions and logic, and communicate effectively with human engineers. In the field of biology, design and build artificial intelligence models capable of simulating complex biological systems and address data quality. Issues such as system complexity and model interpretability, still a major challenge, requires interdisciplinary collaboration and continuous innovation. International cooperation is critical to mitigating risks associated with advanced artificial intelligence. By establishing safety standards, regulatory guidance, and rigorous testing, we can ensure the responsible development of artificial intelligence, thereby unleashing its potential while avoiding unintended consequences. The exploration of returning to basic life, either as a purely biochemical form or through artificially designed nanomachines, Boyman machine, and the ultimate artificial intelligence life to embody. They all represent a profound exploration of the essence of life. From a chemical point of view, pure return to basic life under Earth-like conditions, there are fundamental challenges. Its fragile silicon, strong reactivity with water, and the metabolic challenges of producing solid waste, making it difficult for it to gain a foothold on Earth. However, in extreme environments such as high temperature, low water, reducing atmosphere and flying water dissolving machines, certain properties of silicon may give it survival advantage. This suggests that if silicon-based life exists, it will exist in a very different form and rhythm from carbon-based life. With the rapid development of nanotechnology and artificial intelligence, silicon's role in building artificial life systems becomes increasingly prominent. Nanomachines, especially silicon-based nanoparticles and microactuators, has shown great potential in the medical and environmental fields, able to perform drug delivery, precision tasks such as disease diagnosis and environmental cleanup. Von Neumann's theory of self-replicating machines lays the foundation for building complex artificial systems capable of self-reproduction and evolution. Although out-of-control scenarios such as the Valley of Ashes are generally considered extremely unlikely in the scientific community, artificial intelligence life as the future form of orbital machine intelligence, the lines between computing and biology are being blurred like never before. Neuromorphic computing and practical systems connect living biological neurons to orbit. The emergence of chip fusion. It marks that the development of artificial intelligence has entered a new stage. Its energy efficiency and learning capabilities are expected to surpass traditional machine-based artificial intelligence. Application of artificial intelligence in synthetic biology and genetic engineering, and its breakthroughs in protein folding and drug discovery. Further proof of the profound impact of computational intelligence on the biological field. However, the future of artificial intelligence as a potential life form, fraught with scientific, ethical, and social challenges on whether artificial intelligence can have consciousness, the risk of loss of control due to its ability to self-replicate, and how to ensure that AI's values align with those of humans. These are key issues that require careful consideration. The international community must strengthen cooperation, develop a responsible development and deployment framework to ensure that the evolution of machine intelligence can benefit mankind rather than bring unpredictable consequences. Exploring the life of the machine, more than just an imagination of the diversity of life in the universe, it's also about human intelligence, a profound reflection on creativity and future destiny.